Thanks for coming. This talk is about extreme multi-label classification with an application in the biomedical NLP domain. My name is Sorros. I'm the founder of Mantis. Before Mantis, I studied at Imperial College, Advanced Computing. I've worked as a data scientist for a couple of years in some London startups. Prior to Mantis, I was leading the data science team at the Wellcome Trust, which this project was based on. You can also find me with the username Sorros in a couple of platforms, Twitter, GitHub, LinkedIn. And if you're interested, you can also send me an email. So this is a little bit cut. I hope this is not going to cause problems. But before we talk about extreme multi-label classification, it might be worth doing a quick reminder on multi-label classification. So this is a very similar type of problem as multi-class classification, with the difference that each example can have more than one classes. A typical example of a multi-label problem is setting categories in movies, as we see here. The extreme multi-label classification problem differs on the amount of labels used, which are typically in the thousands or millions. As an example of a problem when Amazon is trying to assign tags into their products, or when Bing is trying to find relevant search queries when you search, or categorizing Wikipedia articles is a type of extreme multi-label classification problem. In practice, Amazon and Microsoft are quite active in this area, in extreme multi-label classification, because they're interested in this type of problems. And Wikipedia is also a common testbed for these types of problems. Another interesting characteristic which you can see is that there is a large vocabulary in these problems of thousands of tokens, which is quite large and adds an additional challenge. So in the biomedical domain, in particular, there is a common problem is that is an extreme multi-label classification. One is assigning tags into biomedical publications. So this is applying MES tags, which are tags like blood pressure, hypertension, essentially categorizing into a very coarse, there are 29,000, so a very fine-grained system for categorizing biomedical publication called MES. And actually, it's the job of expert annotators to annotate biomedical publications when they're indexed to be part of PubMed, which is a database of biomedical publications. So there is the motivation to automate that process. And as a result, there's also a competition called BioAsk that centralizes all this data set, which conveniently exist. It consists of 14 million biomedical publications that are already tagged with those MES tags. And this is the problem I was working on. The vocabulary in this setting is around 400,000 tokens, so it's quite a large vocabulary. So Wellcome Trust, which is where this project took place, is a large biomedical funder, one of the largest in the world. The motivation behind the project was, prior to creating this algorithm, Wellcome had a way of categorizing their grants which was very coarse. It was either the funding team that was giving the research grants to researchers, something like infectious diseases research team or mental health, what you see on the left. So, you know, the colors are just these few categories of the different teams that they're giving grants, and then or the type of money they were giving, such as a scholarship or an individual grant to a researcher, but they didn't have a fine-grained system. So, for example, they couldn't easily say in a standard way how much money they were giving to malaria or HIV or any type of biomedically related disease or theme. So when working with, in this setting, in extreme multi-label classification, there are four main challenges that we have to overcome in order to work around this scale. This is the amount of space models tend to take in disk, the memory you need to load the data and the models as you're training, the time it takes to train, of course, and also inference time sometimes, depending on how you're applying the model. So let's talk a little bit about those problems, starting with the amount of disk space required. So if we want to train a very simple model, like a baseline of a traditional TF-IDF SVM in the kind of setting I said before, so mesh tagging, and we train one individual classifier for each label, which is typical in those cases, then we would have to have one parameter per vocabulary term. We have a large vocabulary term of 400,000, and typically scikit-learn, if we use scikit-learn, uses 64 bits, so 8 bits, so this would require in total around 92 gigabytes just to start one single baseline model, which is quite large and inconvenient to work with. But fortunately, there is an easy way to solve this problem, which is not all of these vocabulary terms need to have parameters that contribute to the classification. Actually, an order of magnitude less parameters are needed most of the times. You can control that. This is just an order of magnitude calculation. But most of the weights for these terms are near zero. You can actually set a threshold pretty easily. You can say, I'm going to zero out all the parameters that are below, say, 0.1, and check whether that affects performance. And then, actually, conveniently, scikit-learn in particular, also for some classifiers, it provides a sparsify function that transforms the parameters into a sparse matrix, essentially requiring only the non-zero elements to be stored, which reduces the size like an order of magnitude less to around 1 gigabyte. So that's one way that you can work with having a reduced size for your models. Interestingly, neural networks in these settings are more compact than a baseline of a traditional algorithm. So for example, if we do a very simple architecture, which is now a little bit cut, but with an embedding for the 400,000 terms, say a 300 dimensionality for the embedding, and then convolution filters, if we maintain the sequence length on 300, most of the parameters, as you see, and then we do a mean pool, and then we do like a linear layer on the dimension of the vector that we represent, say, the grant or the sentence to the outputs we want to classify. Most of the parameters are being consumed by the embedding table, as you see, and the parameter space is low enough for the size of the network to be not too big. So this is interesting and unintuitive. It was when I started working, at least, on this problem. I also want to mention another trick you can use for reducing size independent of sparsifying the parameters, for example, which is you don't have to use a complete vocabulary splitting by some sort of white space. You can rely on subword tokenization, so the same way BERT and Transformers models use, which allows you to, instead of represent each token, represent sub-tokens, subwords, and represent a similarly large vocabulary with a smaller set of terms. For example, in BERT's case, it was using a vocabulary of 30,000. We can use something similar and reduce the size quite significantly, even before considering using sparse parameters, for example. So this is the disk space. Memory, if we actually try to load this data into memory, for example, to do scikit-learn tends to think that things fit into memory sometimes. The target vector alone would be 14 million rows because it's 40 million examples, and then 29,000 columns because it's 29,000 labels. So it would actually be, we don't see it here, but it will be in the terabytes. Fortunately, again, most of these columns are actually zero. Most of the elements, this matrix is quite sparse. Most of the elements are zero. A few elements are non-zero. And if we represent this matrix as a sparse matrix, we can actually load it pretty easily into memory. Again, like it falls an order of magnitude less non-zero elements per example. Instead of 29,000, around 29 tags apply per example. And actually, conveniently, again, you cannot see, but scikit-learn provides a parameter when you're trying to represent, when you're trying to convert this data into a matrix, which is sparse output equals true, and then you can just get your space matrix. So you can actually fit, in some cases, those data into memory. But of course, this is 29,000 tags. And as I said in the beginning, some problems have millions of tags. So if you actually scale that to million, then you run into the same problem. So the typical way, I wonder if we can fix that splitting of the screen at some point. But the typical way we solve this problem of the data not fitting into memory is by not loading the data into memory in the first place. So for example, as I'm showing here, you can just iterate over your data one by one, and you then use that data into batches to train, or one by one. You can train into batches of one, which is typical on what we do when we're doing deep learning, a little bit less typical for scikit-learn, for example. In scikit-learn, though, even though it's not the most common way we do, you can actually use a streaming way of doing this. Some algorithms, like TF-IDF vectorizer, for example, support giving it a generator. So instead of a list, because inside them, even though they don't advertise it, as far as I'm aware, they consume it in a for loop, using a for loop, which means they can consume the iterator instead of, for example, needing like a 7 or 30 gigabytes. If it can fit into memory, doing it with a generator, it would be quite light memory-wise. In terms of classifiers, the typical way we do that in scikit-learn, for example, is with partial fit. And as you can see here, like, it looks very similar to what we do in deep learning. So you have to do the training loop yourself. You have to iterate over your data multiple times. You have to draw on examples, and then you just feed them into a partial fit. And this is, again, reduces the memory requirement quite significantly. And you can stop wherever you want, even when your epochs end, or you can have a stopping criterion exit. Cool, so this is memory. Training time-wise, the situation is a little bit more straightforward, because fortunately, as you know, we have all these different instances in AWS or any cloud provider you use. This is AWS in particular, so usually the most you have to do is just scale with one line change or one parameter change. In scikit-learn, for example, there is an njobs parameter, then you can use as many CPUs as you have available, and you can use bigger instances to get more CPUs. In deep learning frameworks like PyTorch, TensorFlow, it tends to use most CPUs by default. If you want to use a GPU and you want to scale across GPUs, which we had to do for this project, again, most of the times it's a one-line change in those frameworks, so it's a relatively easy way to reduce training time. But there is also one more thing you can do in these settings, and this is called negative sampling. This relies on the fact that a lot of your examples, again, contain, you have a lot more negative examples than positives. In these 14 million examples, you can think that in one column could have a few positives for that label, or maybe 1,000, but not a million. So there are a couple of ways you can do negative sampling, and it's not only a trick being used in extreme multi-label classification, but one way is if you group somehow or cluster, you can do some pre-clustering of your labels so that they're sort of similar. One technique which is going to be used in a model I'm going to show afterwards. If you cluster them so they're grouped in similarly looking clusters, then you can remove all the rows of those clusters that contain only zeros. You can keep only the rows that at least one label is activated on that cluster. And this throws away a lot of the data. And then you can use that reduced data set per cluster to train either individually, one-by-one classifiers, or different neural networks, but with much less data than the original data. And this alone will converge much faster. Okay, and then we have inference time. So inference time is not always relevant and important. So for example, in our case, with the welcome trust, We can predict all the grants that Welcome was giving overnight using a batch job. So that's fine. This was taking some hours still, so reducing inference time is important in some sense, but it's not, we didn't have a requirement to have the algorithm run in real time. Sometimes though you have to have like a faster response. So one trick you can do there is called the binary tree, and it's commonly used in this setting. So instead of learning one classifier to do all the labels, you can, again, as we were saying before, you can cluster, you can do a recursive clustering, you can cluster into 2 or into as many clusters as you want, and then cluster again your labels, creating a binary tree. And then at inference time, if you do that, then you can go, as you go down the tree, you don't have to now do predictions for all the labels, as you would naively have to do, because you have to decide which labels apply. You can actually slowly go and traverse the tree and only do a prediction for, say, a few labels or hundreds, because you're not going to visit the entire tree. Not everything will be activated. You will either go right or left based on which applies. And then a subset of the tree, you will have to actually calculate the probabilities and then say these labels apply, but you skip calculating for a lot more other labels.
Sorry, just very briefly, just to clarify further this binary tree approach, is it sort of similar to divide and rule where you're clustering the data in a particular way such that you can optimize or maybe even parallelize, I'm not sure, the way you're doing the computations?
Yeah, similar, even though I think in this case it's, you have to use like a custom way of doing it. You cannot use some sort of divide and conquer out of the box, I would say. In each layer, I mean, I guess I didn't mention, like a different classifier applies as well. So you have to have, more models maybe than before, because each layer you either have to have one per node or one that like it's a different multi-label classification problem. This is also a technique being used in multi-class classification as well sometimes, because you have to do a softmax over the classes, and then that's quite expensive if you have a lot of classes in ImageNet, for example. So they actually do this sometimes to speed up the softmax calculation. Cool, let's look at some models. So I want to highlight just 3 of the models we tried, and then some techniques used in those models and some additional techniques. So one of the first things we did was create a custom architecture based on literature, which was based on the space, like a framework similar to what space is doing, of embed, encode, attend, predict. The encoding layer was inspired by BERT in the sense that there is a feature extractor and layer normalization after, with a residual connection that we repeat 4 times. And then, of course, instead of multi-head attention, we just do one deconvolution. We actually developed that at the time that BERT was just new. So it was kind of, this was at the time like a good architecture that we started playing with. Then we added hierarchical attention, which basically adds one attention vector per, I mean, it's up to you. For us, we actually, again, inspired from BERT, try to keep the sequence length. So input and output of those layers are the same. Say, for example, 400 tokens and 400 in the exit, same with the hierarchical attention. And then we add the fully connected layer in the end to predict the labels. And this went quite well for a subpart of MESS. So the disease subpart is only 4,000 labels, and this did around 63%. The state of the art is around 70. But we had some difficulty scaling up to the entirety of the 29,000 labels. So this, which you kind of see, is a really interesting work that is now also in production at the Welcome, which is very fast. This is a technique, this is a model from Amazon that is using most of the tricks that I mentioned before. So the way it works is, it's a general framework for how to work in extreme multi-label classification problems. The first thing they do to reduce the size of the problem is to go from, let's say, millions of thousands of labels, they do a clustering to a lower number of labels that they control. So they cluster first the labels, and then they do a multi-label classification model to predict the reduced set of labels, to predict which clusters apply. And that is quite fast because it's on a reduced sample. And in those clusters, they do negative sampling, as we said before, so this goes quite fast. And then after, they only pick the clusters that have been predicted, and on those, they do a final ranking model. So let's say 4 clusters applied that contain its 40 labels. Only for those, they actually re-rank them with a linear model to get the final predictions. Similarly to what we were saying before with the binary tree, they don't look at all the labels, which is quite fast inference as well. They actually do that recursively, building a binary tree as well, but the important details is kind of like this 3-step process. They actually do, this is a linear model, which achieved 56%, a little bit less than the neural one, which is kind of what you get with linear models in that problem that I was working on. But they also have a transformers-based model called X-transformers, which in theory plugs into the second stage. Instead of doing a linear model there, you can do a transformer to produce the clusters, and then that, in theory, works better than linear. In our case, we didn't see that performance boost. But where we did see the performance boost was in this last model we built, which uses another technique which is very common in these settings, which is called multilabel attention. So the way this works in this case is we have a BERT model as we would have, and then we get the outputs, and instead of having, like, let's say, a linear layer that sort of goes from the outputs, maybe with an average or maybe from one of the tokens into the labels, there is one attention vector per label, so separate. That's why it's called multilabel attention, the thing you see on the right, on the left, but on the right of the left graph. One per label, which sort of learns the intricacies of the label to sort of only attend to the tokens that are relevant for that label. And then there is just one hidden layer before you go into a one output neuron to say whether that label applies. This is widely used in the extreme multilabel classification literature for the best performing models. And so we added that on top of BERT, which has already been done before in a paper called BERT Mesh. So we just took the idea from there. And this, again, scaled to all the labels performing around the same as the neural network we showed before, but for all the labels, around 63%. And we also made that model available in the Hugging Face Hub, so you can download it and do predictions. It's quite expensive to train those models, so it took us 4 days with 8 GPUs, and so it takes a little bit of time and a little bit of cost, so you can just skip that and just download the model and use. Cool. There are 2 more things actually you can do in this setting, which is quite common, which sort of boost performance, say around 2% each, which in our case we haven't rolled out, but that are worth mentioning. One is called threshold optimization. So unlike multi-class classification, where you have a softmax and you get probabilities, here you usually have a sigmoid in the end, and you get a probability per output. And then you have a threshold, say, for example, above 0.5, all of these labels are applicable. Usually you have to play a little bit with the threshold because not all examples have the same number of examples, so some get, you know, like the scores you get are not, say, normalized. So you can, for example, do a little bit better if you use a lower threshold mostly, but you can actually do even better if you use an optimal threshold per label. So you go one by one each label and say you try some values for the threshold, and then you check whether that improves the score, and then you do that iteratively because changing one threshold might sort of affect the other labels. So you go one by one, and then you sort of iteratively do that until there's no change, and then you end up with one threshold value per label, which is the optimal threshold value for the for your problem, which is again inspired from a paper that, and the algorithm from the paper is here. And there's also one more thing, which is unsurprisingly doing some sort of ensembling in the end to get a little bit of more boost. The problem, again, as I said, is it's quite expensive to train, say, for example, 4 models or 5 or 3, and then sort of do some sort of ensemble with them. But there is one way you can actually train one model, which is quite interesting and a lot of people use in this setting, and get a couple of models. And this is called snapshot ensemble. And the way this works is you decide you split your training steps say, in 10 different or 5 groups, and then you basically reset the learning rate. You set your learning rate really high every time you reach that, say, 50 steps or wherever you've split your training time. And then this sort of resets the loss. It's like resetting the learning process in a nearby space. So the model sort of converges slightly differently. As you can see from the graph from the paper that has introduced this, it tends to converge similarly, but with producing a little bit different models that if you ensemble them together, you get a better performance than the one model that you would have trained. That's why it's called train one, get M for free. And you can just pick the best performing models from that and combine them together, and you have an ensemble. Cool, a very quick wrap up. So we saw most of the techniques in the literature that are being used in a couple of papers, even though I didn't mention the actual papers, but these are the main things that most of them are doing to actually work in this setting. These are using sparse parameters to reduce the size of the models when they get quite large, using sparse data to be able to work with the data. Stream the data, of course, if the data is bigger than they would fit into memory to begin with, or even regardless, and then using multi-CPU, GPU setups, which we can do quite easily for reducing the training time, binary tree for reducing the inference time. Then we saw multi-label attention, which is a key component of the state-of-the-art in this setting, and 2 tricks, threshold optimization and snapshot ensemble. So what I learned from doing this project, just 3 things real quick, is 1, the first model I presented was like a custom model we created, and initially it made sense because it was inspired from literature. It should be easy to develop and perform, but it actually ended up quite hard. So I guess one thing I'm taking up from this project is that when we're going for a custom model, which nowadays maybe we don't have to do that often because we use transformers and pre-trained architectures, but it takes time to stabilize and make like, especially if you're in edge cases, to get like a stable model performing in your problem. Popular libraries can fail you in edge cases, which refers to the fact that, for example, if you do multi-label classification in scikit-learn, and you're trying to do the TF-IDF SVM baseline I mentioned, then that doesn't work out of the box. For example, you have to do something custom because in that setting of multi-label and sparse outputs and with all these things, there's an open issue that it doesn't work out of the box. You just have to do something else. So sometimes, if you're working on edge cases, again, some frameworks may not work out of the box. Or for example, even with PyTorch or TensorFlow, for me at least, I didn't find an easy way to work with sparse outputs. So the way I went around that is I was converting the sparse Y vector into dense every time I was doing the calculation. And then also a lot of the techniques that I mentioned, I mean, I believe they work, but for me, they didn't work out of the box. For example, threshold optimization, snapshot ensemble, they didn't just work. If you try them, they look straightforward, and a lot of papers mention that they work for them, so I'm sure they work, but I'm just saying that, for me at least, they didn't work out of the box. It's not like you read something and then, 1 week after it works. Cool, so all the code actually is open source in the first link. It's called Grant Stagger, Welcome Trust. I'll share the slides after as well. And we've blogged extensively about some of the things I mentioned here in this talk. But yeah, if you have questions, you can send me an email after or now. Thank you.
Hi, I'm just coming with the microphone. Just if you have a question, please raise your hand.
Thank you. That was a great talk. Quick question just on evaluation metrics in these. What have you found? Is it just the traditional accuracy F1, or have you found sort of specific evaluation metrics are better suited for how these, let's say, data sets are labeled?
Yeah, so what we used were traditionally micro precision recall and F1, and which is also used in the research. But there are actually some specific metrics which I didn't calculate, but they're also reported in this, like there are some hierarchical measures. So in the MS case, this is a hierarchical tree anyway. it starts from a group of 7 tags and then it goes down. So there are some metrics which have been shown to correlate but be also slightly different that take into account the tree. There are also some metrics from retrieval, kind of how good are you in ranking these tags, which some people report. But in all of those metrics, different models come on top. So I mean, for us, we cared a lot about F1, but we didn't calculate any other metrics.
Thank you.
So I had a question about the input text. How long is it in these applications? Is it so long that you can feed the old text even in the neural network models?
So it is around, typically, I mean, so the biomedical publications have a title, an abstract, and then they have the full text.
Yeah.
And typically the data sets use the title and the abstract, which usually falls around 400. Like you use a 400 sequence length and you're fine. But there is some work that actually extends that to the entire text. And nowadays you can do that also with transformers quite easily. You can just use a longer transformer, like a longformer, for example. Or even in the case, of course, of a baseline techniques, that's fine. You don't care. You can increase a little bit the vocabulary just to account for more text, but they work as well. But for neural networks, you can just switch to something that works with longer text.
Oh, sorry. Thank you. First of all, really good presentation. I learned quite a bit. A quick question. Any challenges when you were trying to get this, get the data labeled? I mean, there would have been a lot of data to label, so I just wondered, how was the data labeled, and also two, how much of the data was labeled?
So as I mentioned in the beginning, we were fortunate that actually this has been done for us from these expert annotators that they do this as a living for indexing them in PubMed. So we use biomedical publications and they're already come with those tags. But actually now that you mentioned labeling, I mean, of course, we train on biomedical publications and we apply on Wellcome grants, which is like a slightly transfer here. But so we did label like a subset of Wellcome grants, say around 2,000, with some MES tags that apply. Not all of them, of course, applied for each one. And we evaluated how well the performance transfer. And it was actually doing even better in Wellcome, maybe because we use less, less of the tags are applicable. And for those, it works quite well to differentiate which one is which.
Thank you. I have a question. So basically, you trained on biomedical publications, but you applied it to the grants. Have you investigated adversarial examples where the text is, let's say, engineered to maximize the number of tags one gets, since grants are reviewed only by, like Wellcome Trust, let's say, whereas you train on a very nice data that is not that doesn't have those adversarial examples in it because it's reviewed by, publication, like the conference organizers, committees that would see past that. So you don't have adversarial examples in those data sets.
This is a great shout. So I'm no longer working on these projects, but my colleagues at Wellcome, they're here, so they can take your suggestion and apply it. But we've done a little bit of work on the ethical implications of this because we care about whether, for example, the wrong tags are applied. And we did notice some problems that we try to mitigate, but what you're also saying, I mean, of course, we haven't advertised very publicly to researchers so that they can try to do, optimization on their application, but it's a good shout. We should check that.
Any more questions? Cool. Okay. Thanks so much, and you can catch up with Sorros tomorrow. Good day.